Добрый день, дорогие участники Всероссийской научной школы, Международной научной школы исследования космоса, теории и практика.
Good afternoon, dear participants of Space Development Theory and Practice 2020 Summer Space School.
Сегодня у нас лекция по программе, которую мы прослушаем с вами. Она называется «История освоения Луны», и эту лекцию даст нам старший преподаватель МГТУ имени Баумана, кафедры робототехника и мехатроника Виктор Валентинович Зеленцов, который стоял также у основания этой программы и прошел многолетний путь становления этой программы, вложил в нее большой вклад, и сегодня он попробует помочь участникам также получить знания, которые они приобретут для выполнения коллективного проекта и для своих общих впечатлений о космической программе.
So today we got another lecture on our agenda. The lecture will be given by Viktor Zelentsov. And the name of the lecture is Lunar Exploration History. And Viktor is one of the founders of this program. He works for Robotic Systems and Mechatronics Department of Bauman Moscow State Technical University. And he's put quite a lot of effort into the organization of the summer school since the very beginning. And today he will try to give you some extra knowledge you can apply in your team project studies and also broaden your horizons in terms of the space science and technology. Thank you, Victoria. Let me take the floor. And as I was introduced, I should also mention that I am a product of the Youth Space Center activity because the interest to space I had since 14 was greatly appreciated. And сейчас я еще в конференции?
Да.
Так, презентация. У меня куда-то пропала панель управления. Вот она. Все, сейчас. So at the moment I was disconnected. I wanted to say that I'm a product of the Youth Space Center activities myself, and my interest to space I had since 14 has got appreciated there, and I've got quite a lot of extra knowledge and applied my ideas. And currently I'm doing two things. I'm teaching in Bauman Moscow State Technical University, and I'm supporting International Space Station program as an interpreter and consultant, and sometimes as a photographer, supporting various meetings and supporting the launch campaigns in Baikonur. So I've seen most of the launches of the ISS crews from Baikonur, from the first one till the most recent one. So the reason why we decided to give this lecture is that it's always very important to know what was done before you get down to some kind of project. Reasons for that is that first, you don't want to waste your time and effort when you are working on something new, in case someone has already done that. And second, you should understand the place and role of what you are doing in the general big picture of the area you're working in. So today we decided to talk about an exploration of the moon in its historical perspective. Some of that topic was already covered by Lev Zelenyy when he gave you a presentation on the moon itself. He touched upon some historical aspects of the lunar exploration. Mr. Rebbe gave you an account of Apollo program yesterday. And that made my task a little bit easier today, but I would like to stress some engineering aspects involved with the past lunar missions, because some of the things which were done are extremely interesting, and it's kind of nice to understand them when you're working on something new. So I would start with the moon itself. I will not tell you a lot about it because this has already been done by Dr. Zeleny. I would only tell you that it's been there for billions of years along with the Earth. And when we talk about the lunar exploration, we should take into account two facts. We should take into account the distances between the Earth and the Moon. You can see right here, because you've got to fly that distance to get into the vicinity of the Moon. And the other interesting fact that the period of the orbital period of the Moon is almost equal to its rotation period. So it rotates around its axis at the same angular rate it rotates around its orbit. So we always can see one side of the moon from the Earth. So we've got the direct line of sight on one side of the moon only. We never see the other side with the naked eye. And you will see during this lecture that something has already been done to do that, to give us the access to the far side of the moon, at least from the communication standpoint and from the standpoint of studying its surface. So we've got to cover the distance from the Earth to the moon in order to get involved in some kind of exploration. We want to get close. However, for a long period of time, people were unable to do that, and they believed that the Earth is something round and flat and shiny somewhere in the sky. And the first attempts to study the moon were done with the naked eye, and then with the advance of the telescopes, people started studying the surface of the moon. So Galileo Galilei, famous astronomer, was studying the moon in 16th century, 16th, 17th century, and in particular, he studied the phases of the moon, and you can see one of the drawings here. With the development of the telescopes, it became possible to observe some details on the lunar disk, and you can see that in 17th century some kind of map of the moon already existed, and in particular this is the map developed by the Dutch astronomer. And actually at that time you can find some kind of reflection of travel to the moon in literature, in all kinds of fiction, and sometimes in science fiction. The options to travel to the moon proposed were quite various, from using some kind of paranormal forces like demons, which would take some characters to the moon and back, and using the carriage towed by a lot of swans, to something more or less physical, which was covered in Jules Verne's From the Earth to the Moon, which was launching a crew of 3 in the projectile of the gigantic cannon, which is feasible from the physical standpoint, but which is unfeasible from the medical standpoint, because the G loads developed would be too high for any human to survive it. So that was going on till the mid 20th century, when the first designs of more or less powerful rockets came to life. And here we can mention two individuals who are believed to be the fathers of two great space programs, Soviet space program and American space program. That was Sergei Pavlovich Korolev in Soviet Union and Werner von Braun in the United States of America. Well, strangely enough, you can ask the question if you are familiar with the topic. Braun was German. What did he have to do with the US space program? Indeed, von Braun was a German engineer who worked in the field of rocketry in 1920s, 1930s, and 1940s in Germany. And the group led by him designed the first ballistic missile, which was capable of carrying 1 ton warhead to the distance of 300 kilometers, who surrendered to the Allies in the end of the war, and his entire contingent of engineers moved with him and some equipment to the United States. And although US had some experience in rocketry by that moment, the history developed in such a fashion that Braun became the mastermind of the major accomplishments of the US in that field, at least in 1950s and 1960s. Sergei Korolev, who was a graduate by Bauman Moscow State Technical University, by the way, initially was interested in using rocket propulsion in the aeronautics, equipping all kinds of gliders and even the bomber planes with the rocket engines. However, in the end of the World War II, Korolev was tasked by the government to study the German experience in rocketry, and in particular, he was given a task of reproducing V2 and making it operational with the Soviet rocket forces, which actually gave him a very interesting position because unlike von Braun, it was something he knew already. Someone else's, he could look at someone else's experience, study it, and then understanding all the strong points and weak points, start making his own engineering decision, which actually enabled his group to reproduce V2, to upgrade it, and then finally being tasked with delivery of the warhead to the intercontinental range. Using that experience, Korolev and his group, which was called Special Design Bureau Number 1, were able to develop, let's call it a missile, but it's more famous as a space booster called R7. And you can see the specifications here, which actually could launch 1.5 tons of the payload to the low Earth orbit, which made it possible to launch the first artificial satellite of the Earth called Sputnik. You will see on the next slide. And at one point of this workshop of this school, you will have a virtual tour of our display facility in Dmitrov branch of Bauman Moscow State Technical University, and you will see the actual R7 serial number 11 there. So it's quite an interesting vehicle, which deserves a special lecture. We will not cover its details here because it will take me till the morning to cover the history of the lunar exploration. So let's wait till we have a chance to see it at least remotely. So having this kind of launch vehicle, it was possible to launch the first 3 artificial satellites of the Earth, including that famous Sputnik on October 4th, 1957, and launching something into the Earth orbit is in fact an enabling technology for the further step to launch something towards the moon. And the same kind of step was done a little bit later in the United States of America on von Braun's Juno 1 launch vehicle, which was derived from Redstone missile. And the satellite launched was called Explorer 1. It was way smaller in its mass, but it was small but good. It was good because it enabled James Van Allen to discover the radiation belts around the Earth. So at this point, we can start talking about the lunar exploration, and we'll use this timeline. And in closer to the end of the lecture, I'll give you the source of this timeline. It's developed by a certain educational organization in the US. So the ideas to launch something towards the moon came to life very quickly after the launch of the first Sputniks, because the space programs had some political value at that time, and it was beneficial to fly something new, to fly something further than someone else did that, and make this kind of achievement. So the interest of engineers to launch something towards the moon, and the interest to scientists to study the moon actually coincided with the political interests of the governments in Soviet Union and the United States of America, and those countries started launching all kinds of payloads towards the moon. And let's see what was happening between 1959 and 1957. You can see that the first landers actually landed on the moon. And initially, the landings were very harsh, so the probes actually were colliding with the lunar surface with some purpose. We will talk about that a little bit later. There were some missions to fly by the moon, the mission to photograph the far side of the moon, some lunar mapping missions, and some missions were performed in order to study the properties of the lunar surface while preparing to something even more grand, to take in the first humans to the moon. And here we can just like name the Russian program called Lunar, the US project called Ranger, 3 types of rangers: surveyors, and lunar orbiter. And we'll talk more in detail about the purpose of those missions in a minute. So the capability of R7 was not enough to launch something towards the moon. So the third stage was developed and added to the rocket, and that has increased the payload capability to roughly 4.7 tons to the low Earth orbit, which enabled to launch some interesting missions like the missions to the moon, Mars, and Venus. So the first probes were launched on this kind of launch vehicle. The first idea was to deliver something to the surface of the moon. And at that moment, the technology only enabled what Mr. Abbey called direct ascent last night, which was designing the trajectory of the probe in such a fashion that it would fly into the moon and collide with the moon at one point. And it requires quite a lot of precision, because besides of achieving that parabolic velocity of 11.2 kilometers per second to leave the gravity field of the Earth, you need to be very precise timing-wise and velocity-wise in order to hit the moon at the proper moment. So the first attempt, which was called Luna 1, actually missed and entered the trajectory around the sun, and it was named the first artificial planet in the solar system. And Luna 2 did hit the moon and delivered a lot of little tokens with the Soviet emblem just to commemorate that first so-called harsh landing on the moon. The next and the US flew the same kind of mission. I mean, the mission similar to Lunar 1 with some scientific purposes as well, measuring some physical parameters of environment around the moon, and Pioneer 4 flew by the moon and entered the orbit around the sun in 1959. I would like to spend some time talking about this mission. I told you in the very beginning that we cannot see the far side of the moon with the naked eye. So there was a very interesting job to do it by means of the space probe, and it was accomplished in 1960. So for that purpose, Lunar 3 probe was designed and launched, and the mission involved launching from the Earth. So this probe had already a more sophisticated control system, which enabled it for the mid-course correction to put it on the trajectory where it would be captured by the lunar gravity field and swing around the moon, and then fly back and then leave the sphere of the Earth's gravity influence. How would you take the picture of the far side of the moon in 1960 and transmit it back to the Earth? The TV systems would not work because you would have to televise the video from the far side, from behind the moon, and the moon would actually block your radio waves from into the Earth. At that point, the digital cameras were not available, so you could not snap a picture on your cell phone or digital camera and store it somewhere to transmit it back to download it back to the Earth in some time when you get out of eclipse. So the technique was quite intricate. There was a photo camera which was photographing the far side of the moon. Then the film was developed inside the probe, and then the film was fed into a kind of scanner which was scanning it, turning it into the electrical signal, and that signal was broadcasted back to the Earth. I would like to stop at an interesting point that this is the first unofficial example of the international cooperation in space. The reason is that the film which was required for that kind of mission was kind of special. So some special requirements were imposed on that kind of material, and Soviet engineers searched through the entire Soviet chemical industry and the chemical industry of the socialist camp countries in Eastern Europe, and they couldn't find the material to photograph the far side of the moon. And the answer came from a very unexpected source. It came from the US reconnaissance balloons, which were launched on the reconnaissance mission over the territory of the Soviet Union, and which were easily shot down. So some of those balloons had the payload with the camera, which had the film, which was perfectly suited for this kind of purpose. So the film was unloaded from those cameras. It was tested. It was certified for the use. It was cut and perforated, designated ASHA, which stood for American Balloons abbreviation, loaded into Lunar 3 camera. And the first pictures of the moon were taken by the Soviet probe on the American film. So To give you an example of the imagery acquired, you can see a look at those pictures. You could see that the resolution was kind of wishing to be better, but you can see some features on the far side of the moon. And another interesting point is that the imagery was acquired in the deep space communication facility in Yevpatoria, and it was printed by a teleprinter at that very facility. And the very first picture of the moon was discarded by the operator because it was too noisy and he didn't want it to be that bad. He didn't want that bad picture to become the first picture of the far side of the moon. And people who worked with Sergei Korolev are saying that he was there, he was extremely excited and nervous. And once he received that first good picture of the far side of the moon, he went to his office and started giving names to all those formations on the far side of the moon. So that's why if you look at the far side of the moon, you will see quite a lot of Russian names there, because there is a rule: if you discover something, you've got the right to name them. The third critical step in lunar exploration is actually gaining a capability to fly people to space. And here we should absolutely mention the first human mission in history, which was flown on April 12 by Yuri Gagarin. You can see the data regarding Vostok program. So the mission duration has grown from Gagarin's 108 minutes to 120 hours, and this is when it was actually studied how humans take the space flight environment, how they react to being in prolonged zero-G, and efficiently that gave an answer if you can fly to the moon or not, because in order to fly to the moon, you were supposed to be in zero-G for at least 6-7 days. I will not tell you about the design of Vostok spacecraft because it's another interesting topic. I would only tell you that being the very first manned vehicle, or actually woman vehicle, in history, because the first female cosmonaut, Valentina Tereshkova, flew the same design. It was kind of rough. You had to re-enter at about ballistically, which gave you about 11 Gs on the re-entry, 10 to 11 Gs on the re-entry, and you had to be really tough and brave to fly that kind of vehicle. And indeed, the first missions to space, let's take Gagarin, or let's take the first US mission by Alan Shepard, they did have some problems, and those people were designated pioneers, making justice to what they've done. So here you can see the prototype of the Vostok vehicle used for the electrical testing, and the actual capsule flown by Gagarin. They are on display in Energia Rocket and Space Corporation museum, which we can't visit, unfortunately, but if you decide to come again, we will try to provide you this kind of capability. So this is the US approach to the first human mission. Problem was that the existing launch capabilities did not provide for the orbital mission at the moment, so the decision was made to make the first US mission suborbital, essentially flying the ballistic trajectory similar to the ICBM warhead, and that kind of dictated the technical requirements to the spacecraft, which was to be as light as it's possible. So Mercury weighed 1.3 tons. Astronauts who flew it were kidding that this is not the spacecraft you get in, this is the spacecraft you put on. But it's done its job. It's performed the first US suborbital mission in less than a month from Gagarin's mission, and it performed the first orbital mission by John Glenn in February 1962. And Redstone was used for orbital missions flown by L. Shepard and Gus Grissom, and Atlas, the first US ICBM. So it's kind of interesting that both the Soviet Union and the US used their first ICBMs as the boosters, and we've still got their successors flying, being operational and doing some very important jobs, as you will see later on. So that brings me to the point when from the geopolitical standpoint, the situation was the score of achievements of the Soviet Union was exceeding the US score of achievements greatly. It was happening in such a thing that the US were kind of behind them. This is kind of understandable because Korolev has put quite a lot of margin into R7, making it such a great launch vehicle. And the US had to find some options in Redstone, Atlas, or some other ICBMs. So having the Soviet Union launched the first Sputnik, the first human to space, the first payload to the moon, the first taking the first photo of the far side of the moon and launching the first human to space. People who were leading the US space program had to find something to take care of so that they could stick some kind of priority. And at that point, the only idea to gain this kind of priority was to start working on something very, very complicated in advance and try to lead the Soviet Union accomplishing that task. And I would say it was in 1961 when the decision was made to make the Lunar mission such a task, to make a mission to deliver humans to the moon, such a task for newly formed NASA. And in 1961, President Kennedy spoke in Congress about this kind of priority. In 1962, he made his famous speech in Rice University, saying that we choose to go to the moon not because it is easy, but because it is hard. And the purpose of that was the formal announcement of Apollo program, which was tasking to take US astronauts to the moon by the decade, which was essentially through 1970. And as you can judge from the lecture given to you by George Eby last night, they did succeed in that. But in order to take people to the moon, a number of tasks were to be accomplished. The lunar surface was to be studied, at least from the mechanical standpoint, to understand how the landing would take place. The selenography was to be studied as well, because it was absolutely critical to know map the moon and pick the landing sites to ensure the safety of those landings. And that called for a set of tasks of the automated studies of the moon, as well as some human spaceflight studies, which was being able to dock, being able to perform an EVA, being able to stay in space long enough to endure that kind of mission. And as you could see in the timeline, there was a number of projects in the US which were targeting the preparation to the landing on the moon. And Ranger was among them. In particular, as you could see in the timeline, Block 1 Rangers were involved in taking the remote sensing data of the moon. The low resolution imagery was produced here. Ranger Block 2 was actually delivering the payload to the lunar surface, which was a seismometer covered in this kind of impact limiting case, which was decelerated prior to hitting the lunar surface by a rocket pack activated by a radio altimeter. Ranger Block 3s had actually another interesting task, because the higher resolution imagery was required to pick the landing sites. And at that point, the capabilities of the TV systems did not really allow for doing that while staying in lunar orbit. For that reason, this kind of probes were launched on a kind of the suicidal mission. And the idea was that the TV camera, so the probe was launched on Atlas Agena, and it had a TV camera, and it was broadcasting its picture while flying straight into the lunar surface, and basically until it was colliding with the lunar surface. And you could see a number of missions flown by by Rangers flown at that time. That was to provide the data to pick the lunar landing sites. And this is the example of the images Rangers were given. So 3 missions gave about 17,000 images. Another critical step in the human spaceflight, which made us closer to the moon, was done in March, on 5th of March 1964, performing the first extravehicular activity that was done by Alexei Leonov with the support of his mission commander Pavel Belyaev, and it was a success. You will be watching a movie called The Time of the Pioneers, which is like an attempt to cover the events of that mission. The same kind of tasks was performed by means of Gemini spacecraft, with the only difference that the purpose of Project Gemini was quite transparent. It was to develop all the technologies which were required for the human mission to the moon, namely dockings, extravehicular activities, long duration space flight of, as far as I can recall, 17 days, flown on one of the Geminis by Jim Lovell and Frank Borman. And this was done by Gemini to give enough sufficient data to and develop the technology essentially for which was later on used by Apollo. The first soft landing on the moon, staying soft, meaning that the probe stayed intact and was capable of performing its tasks upon the landing, was done by the Soviet probe called Lunar 9. And you can see the lander here and the probe itself. So there was essentially a delivery stage, which was delivering this lander to the circular orbit and then deorbiting it. Providing the final deceleration prior to the separation of the 100-kilogram lander. And the lander was inflating a balloon around itself. This balloon, to perform the role of the shock absorber, which would let the lander leap on the moon for some time, and then the balloon was discarded and the probe would stand upright because of the low center of gravity and take some photographs of the lunar terrain around. So as you could see, the mission itself, yeah, I actually was wrong saying about the circumlunar orbit. It was the direct ascent mission, but it required several trajectory corrections to land at the desired point of the moon. And you can see it right here. So the landing itself was on February 2nd, 1966, and it was followed by a couple of landers of the same design. Here you can see the panoramas, which were shot by this very camera, transmitted to the Earth using those antennas. So, and here is the example of the by Lunar 9 and the subsequent missions. Another project to cover the lunar surface mechanical and chemical properties was called Surveyor. 7 missions were flown between 1966 and 1968, launched on Atlas Centaur, which was another interesting and essential step in the US space program, because Centaur was the first upper stage which used hydrogen and oxygen, giving it higher performance, and being able to use this kind of technology appeared to be critical in taking humans to the moon later on. So the mission of Surveyor was as follows. It was to land on the surface and study the mechanical properties by means of digging the surface with this kind of manipulator arm, which is believed to be the first robotic device used in space. It was to deploy the spectrometer on the lunar surface to find out its chemical composition, and this kind of data were obtained on the lower resolution mapping of the moon was performed by lunar orbiters missions between 1966 and 1967. And interestingly enough, this pod having the cameras was using the same technology Lunar 3 was using to photograph the far side of the moon. It was the limitation of the sensing electronics at that point that the photographs were to be taken, developed on board the probe, and then scanned and transmitted back to the Earth. And as you can see, the imagery obtained was already of fairly high details. So the first pictures of the Earthrise were taken, and you can see that the resolution is fairly decent. So you can actually Google lunar orbiter, and you can find a collection of the images acquired by that, and you can find all those details there. So here we transition to the, and I should mention that all those lunar probes you've seen in the previous segment of the timeline, they were also performing the tasks similar to the ones performed by Ranger, Surveyor, and Lunar Orbiter. So, and at this point, the so-called lunar race came to the full swing. It actually entered its practical phase when there was a race to about who's gonna land the crew on the moon first. And yesterday you were told how it was done in the US. We're gonna look at the big picture now. So at that period, you could see that there is a number of Apollos flying, a number of landings made by Apollo. You can see the last surveyor here. You can see 3 zonde missions, unfortunately unmanned. And you can see a number of the Soviet probes, the first 2 rovers delivered to the moon, and a set of the lunar soil sample return missions. So speaking of zonde, I would give you the introduction to what was going on with the man on the moon in the Soviet Union. 2 programs were developed. One of them was targeting the fly around with the manned vehicle. The other one was targeting the landing of the crew on the moon. These were 2 separate programs. There was a number of political reasons to do that. And to my mind, it was not beneficial for the final outcome of this kind of program. But speaking of technology which was developed, it was decided to use the launch vehicle called Proton, which is still operational and was capable of launching 21 ton into the low Earth orbit. To launch this kind of cluster into the low Earth orbit, and it consisted of Block D upper stage and Zonde or L1 spacecraft, which had a capsule with 2 crew members, which would which would insert itself into the trajectory towards the moon, make several corrections on the way to the moon, swing by the moon, and come back at a very high velocity, which required a special re-entry technique. You can see that the mass of the entire system was close to 20 tons, and the program involved 5 missions flown in 1968, 1970. And I would mention that Alexei Leonov, who performed the first EVA, was meant to be one of the crew members for L1. Here is the mission profile. The launch, which was followed by insertion to the translunar trajectory with the mid-course correction, lunar flyby, and then 2 more trajectory corrections to put you on the right trajectory to re-enter the Earth atmosphere, discarding the service module of the spacecraft and the re-entering. The re-entering was done in a very intricate technique because the capsule was flying very fast, and in order to decelerate and hit the and land in the desired region of the Earth, it was required to submerge into the atmosphere and then jump out of that and then jump back in. And that second re-entry was actually the final one. So it decelerated, deployed the parachutes, and landed. So I would say out of those 5 missions, the practical ones were Zone 5, Zone 7, and Zone 8, which actually had the capsules flown around the moon and returning to the Earth. They were not flown empty. Zond 5 is associated with flying some test subjects inside, including some worms, some I think flies, bacteria, and 2 turtles, which were put into the capsule by the technicians before when the capsule was finally integrated with the launch vehicle, and the turtles survived that journey. And of course, the legacy of Zond is taking quite a lot of the great photos of the moon and Earth, comparable to the ones given by Apollo. So the first Soviet photo of the Earthrise, the moon, some details, and unfortunately the flight testing was not going that perfectly, so no decision was made to put the crew on board Zond spacecraft, although the other representatives of the humankind did get on their journey from the Earth to the Moon. Here I mean Apollo project. And if we touch upon the technical challenges of that, it was resolved by building and thoroughly testing Saturn V launch vehicle, which weighed close to 3,000 tons, and developing the system of the service module, command module, and the lunar module. You can see the characteristics of those vehicles here. And summing up, Apollo project, I would say 17 missions, including 11 manned, were flown between 1966 and 1972, which resulted in 6 landings on the moon, and humans spending up to 75 hours on the surface. So in total, 12 Earthlings, 12 astronauts visited the lunar surface, and the first landing took place on, pardon me, I think I'm wrong here. It's not 20th of April. I think it's 20th of July, 69. So to give you the scale, so Saturn V, which was to be transported to the launcher, actually on its launcher table to the pad, along with the service tower. And to compare the size, you can see the truck and the bus here. And the assembly facility was built, which was able to fit 2 of those systems inside. And speaking of the most significant missions in Apollo project, I would like to mention Apollo 8, which was competing with Zond. So it was not clear whether the Soviet Union would put the crew on board of Zond spacecraft. So after Zond 5, the decision was made to fly Apollo 8 around the moon with the crew. And that crew was Jim Lovell, Frank Barman, and Bill Anders, as far as I can recall. And that mission was flown on the Christmas Eve of 1968. So that was the first human mission in lunar orbit. And of course, this was mentioned yesterday. So the first crew of which landed on the moon, Neil Armstrong, Buzz Aldrin, and the lunar module, the command module pilot Mike Collins. Here is Buzz Aldrin on the moon, and one of the first tracks left on the moon. And the last mission to the moon so far, which was flown by Apollo 17 by the crew of Gene Cernan, Ron Evans, and Harrison Schmitt. It's kind of interesting to mention that Harrison Schmitt was the only scientist who made it to the lunar surface. So he was a geologist by his education. So he actually inspired quite an interesting training program for the Apollo crews to study the geology and to be able to determine what kind of interesting samples to pick, which formations to pay attention to, and that actually increased the scientific value of Apollo mission results. And here is one of the photos of Apollo 17. So by that time, the rovers were available for Apollo crew members, so they could travel around the surface. And speaking of results of the Apollo project, besides of that fact that it was the program which brought the first people to the moon, it gave a lot of information about the lunar surface, both from the imagery standpoint and from the standpoint of bringing the geological samples back to the Earth and understanding the nature of the moon. The Soviet approach to taking taking humans to the moon involved N1 launch vehicle, which was approximately of the same size and mass to that of Saturn V, although the payload capability was not that high due to some facts I'm going to tell you about in a minute. And the system actually involved the three-staged launch vehicle, another stage to put the expeditional complex into the translunar trajectory by means of block D. Then block D was used for the mid-course correction and deceleration of the lunar lander called LK prior to the landing on the surface. And the lunar orbital craft was meant to be an equivalent of the command and service module to take the crew to the moon and stay in some time in orbit around the moon and take the crew back to the Earth. Why did we need all those stages, and why the payload was so less than the one of the Saturn V's? Before I get to that subject, I would like to mention that we've got the lunar lander of that program. We've got an LK in our display facility, and you will be getting a virtual tour of that facility. So one of the reasons why N1 was so underpowered is that we didn't have the hydrogen oxygen propulsion technology at that point, at least at the operational level. So kerosene and oxygen propulsion was to be used on all the rocket stages besides of the service module of LOC and the propulsion module of LK. So which actually decreased the payload capability of the rocket. The second problem was that there was no rocket engine which would provide enough thrust for this kind of launch vehicle. Say Saturn V was using a cluster of 5 F1 engines on the first stage, and we didn't have the equivalent at that moment, so we had to use 30 smaller engines on the first stage of N1, which is kind of okay nowadays for Falcon Heavy, but at that point the control systems technology did not really enable the reliable control and monitoring of this many engines. So despite of being able to build N1 launch vehicles, all 4 test flights of this rocket ended up with the first stage failures, ranging from engine shutdowns to the explosions. And when the rocket was close to its mature state, Neil Armstrong has already stepped on the moon, so the political value of the N1L3 program has got close to 0, and the decision was made to close the program. Nevertheless, this lunar orbital vehicle was developed, and there is an information that it was flown on it was flown on Proton launch vehicle once or twice for testing purposes, and it was attached to N1s during all those test missions. A lunar lander of a very interesting and authentic design was developed. I would like to stop for a couple of minutes at LK here before you see it in the display facility or during the online tour. Unlike a lunar expeditional module having the descent stage and ascent stage, LK only had 1 rocket stage. Due to 2 facts. The initial deceleration was provided by Block D rocket stage, which was discarded after its burn, and the Block E propulsion module was only to fire for a short period of time right before the contact with the surface for the final deceleration and picking the landing location if it was necessary. And then it was actually to perform the function of the ascent stage. So the same rocket pack was used for the descent and ascent, which is the principal difference of LK versus lunar expeditional module. You can see the characteristics, you can see the mass, you can see sizing. You can also see that it was flown by only 1 crew member. So having 1 crew member landing on the moon was not from the way we put it in Russian. It was not because the life was good. It was because 90 tons payload capability of N1 was only enabling to take the crew of 2 to the circumlunar orbit, and 1 of the crew members was to stay in the lunar orbital craft, and the other was to make a landing on the moon. However, it gave another reason to cancel the program, because 1 person EVA on the lunar surface is extremely unsafe, and wearing a suit with the life support backpack on your back shifts your center of gravity to the rear, and if you fall on your back, the chance to get upright is very limited. So it was another reason why this program was canceled. Two LKAs were tested in the low Earth orbit by means of launching them on Soyuz launch vehicle, and they actually simulated the descent to the lunar surface. Although they were altering their orbital altitude, they were actually deboosting them, and their trajectory was measured to see if everything was going on instead of landing them on the moon. But it drives me to the conclusion that the components like lunar lander, lunar orbital craft, Block D rocket stage, this spacesuit called Cratchit, they were ready for the mission, and they found their use afterwards. But the weakest point was the launch vehicle, and I think there were some engineering and political problems associated with that. For example, that technical / political problem of developing the highly powered kerosene oxygen rocket engine, which resulted in the use of very smaller engines. The engines were actually quite good, and they were preserved, and Antares launch vehicle was flying using those engines till that critical failure when they were swapped to RD-181. The decision not to do the static testing of the first stage and was also kind of critical for the program, because as we could see, all the failures were taking place during the first stage powered flight. So sad but true, but Soviet cosmonauts didn't make it to the moon. It was a great frustration of Alexei Leonov, who was also training for that mission, but he didn't make it. So instead of, and at that point, it was decided to close the program and to make it classified and take another course, saying that we not risk human lives. We study the moon by the optic disease. And a number of soil sample return missions were flown to the moon. And here is how it was done. So you can see the indexes of that Lunar probes, and you can see the probe on the right. So the probe consisted of the lander itself and the ascent stage, which was equipped. So the lander was equipped with the manipulator arm, 3 degree of freedom manipulator arm with a drill, which could drill the surface near the landing site, and then eject the soil sample into the capsule on top of the ascent stage. And this sequence is shown here. And after that, the ascent stage would launch from the surface of the moon and fly directly toward the Earth, where it would re-enter and bring the soil sample to the Earth. Interestingly enough, the soil samples from Luna 16, I think 20 and 24 were exchanged with the Apollo samples, and it was proved that the chemical composition of them is identical, so no one has cheated flying to the moon or bringing the soil samples without any participation of the humans. So another 2 missions flown under the same philosophy were actually very interesting. That was bringing the first remotely operated robotic devices, mobile robotic devices, to the surface of the moon. And here I mean Lunar 1 and 2 lunar rovers in 1969 and 1973. And as you can see, the size and the mass of this kind of vehicle compares to a small car. The purpose was to do the visual, I would say, visual reconnaissance of the lunar surface, to study the physical properties of the surface, and to conduct some experiments in terms of measuring the distance between the Earth and the Moon. While we are looking at this vehicle, it says Lunar 3. Indeed, the third rover was planned to fly to the Moon, but then at one point this mission was cancelled because the Proton launch vehicle, which was required to the Moon, was used for another mission to Venus. And the mission profile, the landing profile you could see here, it was the powered descent on the descent stage, and after that the ramps were deployed and the rover would drive down to the surface via one of the ramps. So Lunar 1 traveled 10.5 kilometers on the Moon, and Lunar 2 made 37 kilometers on the Moon. Another photo makes it possible for us to see the design. So there was a pressurized container which was housing the avionics, and the rover was equipped with the solar, with the cover, covered with the solar cells, which would give electric power during the lunar day, enabling the rover to operate. The top of the instrumentation compartment was arranged as a thermal radiator. During the lunar day, during the lunar 9, the lid would cover and prevent the radiator from functioning and rover from the overheating. And the heat was provided by the radioisotope thermal generator mounted in the tail of the rover. As you can see, 8x8 mobility, 8x8 chassis was used. Due to the fact that the cross-country capability of this kind of mobile platform is close to the capability of the tracked vehicle, but the tracks were unfeasible for the Moon because they tend to slip off, and in case of the track being jammed or slipping off the guide rollers, there would be no one to take care of those tracks. The wheels give you pretty much the same dynamics, but they are free of those problems. So in order to communicate to the Earth, this directed antenna was used, and here we come to the control technique. It was fully remotely controlled vehicle. The delay of the radio signal propagation between the Earth and the Moon was creating a huge difficulty, because imagine that you are driving a car and you hit the brakes and it starts braking in 3 seconds, and only in 3 more seconds you can see that it started braking. So every lunokhod had that remote operating crew which was stationed on the Earth. That delay was a huge human factor problem. So every crew worked at the 45-minute long shift and then was relieved by another shift. So there was a driver, an engineer, a navigator, and directed antenna operator and the commander, which were controlling lunar hods remotely. And here are the examples. So there are, speaking of the payloads, you can see those cameras. So the scanning panoramic cameras, which this one can scan vertically, this one can scan horizontally. And you can see the examples of the panoramas provided by those cameras. So speaking of the subsequent period, there was a gap in any kind of missions flown towards the moon till essentially between, I think, 1976, when the last, when Lunar 24 conducted the soil sample return mission, till 1990s, when the other players got involved. For example, Japan got involved with their first orbiter called Hiten. We can talk about it a little bit later. The US flew a very famous mission called Clementine. A lunar prospector was orbiting the moon between 1998 and 1999. And ESA flew Smart 1 in early 2000s. Here you can also see AsiaSat. AsiaSat was in vicinity of the moon, but it didn't have the purpose of any kind of lunar studies. And the problem was that it was the communication satellite for Hong Kong, launched problematically, failing to achieve the geostationary orbit, so which was bought off from, which was insured. The Hughes aircraft, I think, was the design of the satellites. The satellite from the insurance company, and they used some of the trajectory design tricks using the lunar gravity to accelerate the satellite and put it into the desired geostationary orbit point location, and sold the satellite to the other customer afterwards. So let's talk about the spacecraft involved. So Hiten was essentially the first attempt of Japan to launch something towards the moon. You can see the objectives here. You can see the properties of the spacecraft. It's interesting enough that it was deploying a sub-satellite while flying its mission. And it visited L4 and L5 Lagrangian points afterwards, and after that it was deorbited and crash landed on the moon, making the first Japanese object which reached the moon. Clementine, I think it's one of the iconic missions in lunar exploration, because you can see it's a very small spacecraft. Interestingly enough, was developed, as far as I can recall, by the Department of Defense of the United States of America as a technology demonstrator, essentially a spacecraft to try various new concepts. And it was the lunar orbiter with the primary purpose of mapping the moon. So as you could see the timeline, actually no, it was only flying within 1994. However, having those experiments on board, having an altimeter, a radar, a set of cameras, it actually gave quite a lot of imagery, a spectacular and valuable imagery of the lunar surface. And you can see the sunrise over the moon. You can see the surface of the moon. You can see the mosaic images built out of Clementine imagery. And I think that imagery was extremely valuable in terms of planning subsequent missions. And the resolution sometimes was very high. So this is Tycho, as far as I can recall, and this is Tsiolkovsky crater. And here are the links to the resources which would give some imagery and some information from that mission. Another interesting mission, which was the first polar orbiter to cover the polar regions of the moon, which was called Lunar Prospector, flying in 1998, 1999. Its major idea was to study the chemical composition of the lunar surface, thus all those spectrometers. And it had another purpose. It had a purpose of crashing into the lunar surface and being observed from the Earth, trying to find any proofs that there is some water ice on the south pole of the moon. And that's why this kind of probe, this is an impactor probe, which was to meet the lunar surface when the prospector was deliberately deorbited and hit the vicinity of the South Pole. So here you can see the launch on Minotauros and all the maneuvers and insertion into the polar orbit. So to make the long story short, it was an interesting mission. But the final result was not achieved. It did crash into the surface. It did pick up a lot of debris, but the evidence of water was not found. Another interesting vehicle which was flown, not by its purpose, but by the way it was flown, is Smart 1, which was designed by European Space Agency and built by, I think, Swedish Space Corporation or something of that sort. And the idea of that mission was to check the concept, whether you can get to the circumlunar orbit using the electrical propulsion instead of the traditional chemical propulsion. And then after the insertion to the lunar orbit, it turned into the lunar remote sensing spacecraft. So you can see all the instruments here. You can see the design. It had the ion engine, and it had some chemical thrusters for the attitude control purposes. It had solar arrays, and here is the trajectory Smart 1 was flying. So it was launched from the Earth, and then using the electrical thrusters, it was very, very slowly accelerating itself till it was capable to perform the change of orbital plane maneuver, and then it kept spinning itself up till it got into the sphere of gravity of the moon. And then he used the same thruster to decelerate itself and put itself into the orbit around the moon. So I told you that it was the remote sensing spacecraft. So here are the examples of Smart 1 images. Tycho again, and it was a very interesting mission, which actually gave the proof that you can not only use the chemical propulsion, you can fly using the electrical propulsion. It will be slow, but it will take you to the moon. So here is the final segment of the lunar exploration timeline, which was published on the resource I've got here. it's an educational organization called USRA. So the final segment takes us to the period between 2007 and present days. And you can see that quite a lot of activities is going on in that field over that period. And Japan continued their efforts to study the moon by the spacecraft called Kaguya, which was a part of the larger program called Lunar, which was meant to continue afterwards, but came to some kind of hold. Japan, actually China, has become a player in that lunar game, launching 2 Chang'e probes, Chang'e orbiters, Chang'e 1 and Chang'e 2, which were very interesting, and they were the elements of the longer going effort in lunar exploration, because Chang'e 1 was a lunar mapping orbiter. Chang'e 2 did the same job, but afterwards it performed a very interesting journey to the L2 liberation point to check the capability to fly the vehicle there and to be able to control it. And then afterwards it was sent to this trajectory around the sun and made an encounter with one of the near-Earth asteroids at one point. The reasons why it was done to enable to develop the technology for Chang'e 4 mission. We're going to talk later in this lecture about. But you could see that this is the period when China started developing their program, which is targeting delivering the soil sample later this year. So, besides of Chang'e, we can see an Indian probe called Chandrayaan 1, which flew between 2008 and 2009, and it was also a remote sensing mapping probe, which gave some interesting data, which actually was the first object to the first probe to give the material proof of Apollo landing on the moon, because it did capture Apollo 11 landing site. It was followed by Chandrayaan 2, which was a system of the orbiter and the lander last year, but the landing failed. There was a series of US missions flown there at that period of time. You can see a lunar reconnaissance orbiter. We'll talk in more detail, which is a remote sensing spacecraft, which gave huge amount of data about the lunar surface it's sometimes at the almost impossible resolution, and it gave some very interesting images. The experiment called GRAIL involved in 2012, involved 2 identical spacecraft in the lunar orbit with the goal to study the lunar gravity field and its anomalies. So essentially being tracked by each other and being tracked by the Earth. The anomalies developed by the variations of the orbit of those 2 vehicles were studied, and that gave some data about the mass concentrations, gravity wells on the moon, and it actually managed to clarify the information on the thickness of the lunar crust, which appeared to be thinner than it was earlier believed, so about 40 kilometers instead of 60. There was a vehicle called Lady, flown in 2013, and Lady was a mission to study the chemical composition of environment around the moon, the presence of various elements in the near lunar environment. Another interesting mission, which was by NASA as well, is called Artemis. Don't mistake it with the name of the current lunar human space project. To be exact, it was Artemis P1, and that was the mission to fly to L1 liberation point, establish the orbit around L1 for some time, stay there for some time, and then fly over to L2 liberation point, entering the orbit around the liberation point. Why it is required, why it is so valuable, you will see when we talk about Chang 4. And we're going to talk about Chang 3 lander, Chang 4. There are some missions which got cancelled because the original idea of the new approach to the to taking humans to the moon by NASA was initially developed and then changed. So you can see the test flight of Ares-1 launch vehicle, which was one and only flight of that vehicle, and Delta IV Orion test mission here. But we'll get into the detail of, a little bit later. So you can see that originally the idea was to fly Lunar 25 around 2020, but now it's slipping by about a year. And you can see the Orion exploration mission 1, which is going to slip to the right to late 2021. So let's go into the detail. So Kaguya spacecraft, or Selene-1 spacecraft, was the Japanese lunar orbiter, which was to provide the first high-definition video of the moon, along with doing some spectral studies, the physical studies of the environment around the moon. It actually was a fairly complicated mission, deploying 2 sub-satellites, you can see here, and then putting it itself into the final orbit around the moon. And the examples, these are the stills of the video Kaguya was broadcasting. And due to having the laser scanner, it also enabled to put together this kind of 3D models of the lunar surface. I think you can see the Hadley reel here. Speaking of the Lunar Reconnaissance Orbiter, you can see the spacecraft itself. It was launched on 18th of June 2009. So its total mass is 1.7 tons. So the spacecraft itself weighs 800 kilograms. It was clustered with the other spacecraft called L-Cross. We're going to talk about in a moment. So LRO carries those payloads on board, mostly the imaging payloads. This is the concept of LRO in orbit around the moon. And I should say that's the most comprehensive and detailed source of information on the lunar surface these days, because you can see those mosaic images of the near side and far side of the moon. There is also a virtual globe of the moon. You can find at this URL, because essentially you could see the surface with the resolution of up to 100 meters on those globes. Another interesting feature is the special mode, which gives 0.5 meter resolution, which enabled to photograph Apollo landing sites. And this is Apollo 12 landing site. So you can see the lander here, you can see the footpaths, you can see the Apollo Lunar Surface Experiment package laid out. You can see Surveyor 3, the crew of Apollo 12, walk over to and dismounted the TV camera to bring back to the Earth. So this is just like a representative photo of the Apollo landing site taken by LRO. Besides of that, besides of photographing all Apollo landing sites, it also gave some proofs of lunopods still being on the moon, and it gave the photographs of Chang 3 and 4 landing sites. So here we are interested, and that concerns not only the lunar exploration but the Martian exploration. So the technology we as the humankind have got enables us not only to land on, say, Moon or on Mars, but to monitor the progress of those landings visually, besides of being able to monitor the telemetry. So the same examples took place on Mars when the landing of Curiosity rover was toward by I think Mars Reconnaissance Orbiter or some other orbiting vehicle, and you could see the details to like the air brake shield or the parachute laying on the Martian surface. The reason why I mentioned that LRO was launched together with another very interesting spacecraft is that indeed it was launched again on Atlas launch vehicle with Centaurus upper stage. So see the launch vehicle which launched the first orbital human mission in the US history, being upgraded, still retained same. And Centaurus stage, which was used at the eve of the lunar exploration, are still used. And between Centaurus and LRO, which was mounted here, was a small spacecraft called LCROSS, Lunar Crater Observation and Sensing Satellite. It was another heroic space probe, which actually sacrificed itself for gaining very interesting information, I would say kind of critical information for the further lunar exploration. The idea was that after releasing LRO, Centaurus and LCROSS would deorbit themselves, and they will fly on the collision trajectory towards the vicinity of the south pole of the moon. And the Centaurus stage would collide with the moon and make an impact, and that would bring up a lot of material from the lunar surface. And then LCROSS would fly through the cloud of those debris, and using its instruments, it will try to determine the chemical composition of those of that cloud, which was ejected as a result of the collision of Centaurus with the surface. And the purpose was to see whether there is some water in the ice form on the south pole of the moon or not. And here you can see L cross mated to the transfer compartment. You can see the specifications. You can see like 5 cameras, 3 spectrometers, photometer, lots of stuff, the 8 thrusters for the attitude control and all that sort of things. And of L cross is 834 kilograms, so it's quite a substantial payload. So this is the artist concept of how that mission would take place. So this is Centaurus flying towards the lunar surface and hitting the moon. And indeed, so after being launched along with Lunar Reconnaissance Orbiter, this mission made an impact on the moon on 9th of October 2009. And like first Centaurus impacted the moon, and then in 4 more minutes it was followed by the L cross, and the result was there is water ice nearby the south pole of the moon. What was not accomplished by the previous experiments was accomplished by L cross, and later, so it was calculated that impact has brought up about from the various estimates from 160 to 300 kilograms of water from the surface into the near moon environment, which was registered by L cross, and which inspired everyone to land in the south polar regions, established the lunar bases there. And in particular, I believe Dr. Zeliony told us that in the long run, we are starting from the South Pole on the moon by, it's kind of hard to recall the index, either by Lunar 27 or not, for that drill the lunar ice and not to contaminate it by the drill and then to deliver it back to the Earth is being developed right now. So talking about the moon, I can't really avoid talking about Orion, which is a part of Artemis. Moreover, it was depicted on the lunar exploration timeline. So Orion is the new, is a crew exploration vehicle developed by NASA, and it consists of the crew module and service module and the escape system, and it will be, with the mass of 25.8 tons, it will be capable of flying the crew of 4 towards the moon, and the lunar lander is being developed for this kind of project, along as there is an idea to build a space station, man-tended space station at the L2 liberation point. And once we are talking about the history, the only historical mission we ran so far is the test mission on Delta IV rocket on December 5th, 2014. And it flew a very highly elliptical orbit to be able to demonstrate its capabilities in the high radiation environments passing through the Van Allen belt, and that mission was a success. So I promised to talk about the most recent Chinese lunar exploration program missions to the moon. And initially Chang 3, which delivered Chang lander with U2 rover to the near side of the moon, was flown in 2013. And the rover's mass is 140 kilograms, so it worked for some time. At a certain point, there was a failure of the mobility system or the motion control system, but the actual rover lived way longer. And Chang 4 is, I would say, a unique mission. Its designers can be proud of. It's delivering the first rover, or I believe the first functioning lander to the far side of the moon and being able to operate that. How do we operate the vehicle on the far side of the moon when we can't transmit directly there? We need to establish some kind of relay satellite or a system of relay satellites in orbits around the moon. However, the more elegant way was found, which gave the capability to talk to the lander actually as much as the ground facilities permit. The idea was to put, and it was implemented, to launch the relay satellite into the orbit around L2 liberation point. So QQIAO was launched on 20th of May 2018, and I think later this year, in fall, in September, it has put itself into this orbit. So it's rotating around the liberation point, and therefore, so the orbit is actually shaped in such a way that we can see it from the Earth, and the Earth does not, the moon does not obscure the visibility of the line of sight on the relay satellite. So and then in December 2018, the actual lander was launched, which has put itself on the lunar surface on the far side of the moon in January 2019. Same lander and rover used, same design, because originally Chang 4 lander and rover were the backups for Chang 3. And currently everything is working on the far side of the moon. Here is the LRO image show lander and the rover, and the actual photos taken, photo of the rover taken by the lander and photo of the lander taken by the rover. Besides of that, the lander is capable of making panoramas. So this is one of the panoramas it gave. So you can see the terrain surrounding the lander and the UE-22 rover. And at this point, I'm about to conclude my presentation. I believe I picked the most interesting examples of the vehicle's most vivid experiences of the lunar exploration. Although I skipped some of the missions, and I started my presentation with Galileo Galilei, studying the moon via the telescope. I would like to conclude it with Galileo as well, but this is the other Galileo. This is Galileo probe, which was launched by NASA towards Jupiter in 1990s. And during the initial phase of the mission, it captured those two images of the moon. So at this point, I would like to conclude my presentation, and I'm open for questions. Okay, so I can see the hands risen by Curtis Clark.
Hello, I'm Curtis. I have a question. I noticed that a lot of the Russian rockets have very small nozzles. Is there a reason for that?
Well, if you compare it to, say, both yes and no. If you talk, yeah, you might be right. So your observation might be right. If we talk, for example, of R7 or N1, but N1 is an extreme case of that. So the traditional way to design rocket engines for the first stages in the Soviet Union and Russia is to cluster the combustion chamber. So the smaller chamber makes it way easier to test it, for example, and way easier to design it. And by clustering, say, 4 combustion chambers and using a single turbopump to feed the propellant to the combustion chambers makes it kind of easier to design and test the engine, and I think this is the purpose. However, if we talk about, say, for example, Angara launch vehicle, right? We are using RD-190 engine for that, which has got a single chamber and single nozzle. So if your question was inspired by N1, which had 30 engines, the reason was that when Korolev was conceiving that project, he actually wanted less engines, less bigger engines, but he had some controversies with the the leading designer of the rocket engines in the Soviet Union, Valentin Glushko. So actually the requirements of Korolev kind of controversed the technical interests of Glushko at that point. So he kind of refused to design something which would be similar to F1 used on Saturn V, although it was kind of unaccomplished job for Glushko for a very long time. So in 1980s, 1970s, 1980s, he did that. He actually built the most powerful kerosene oxygen rocket engine called RD-170, which was used on Energia launch vehicle, and which is still giving its legacy because essentially, if you talk about the engines used on Atlas V, Atlas V is using the essentially half of RD-170 called RD-180 with the new turbopump on the first stage, and Antares is using so-called RD-181, which is a single chamber of that engine with the special turbopump. So coming back to N1, so Glushko refused to build the huge engine similar to F1 engine, and another design organization led by Kuznetsov was picked to develop those engines. They only had an experience of designing making 2 designs of those engines at that point. So plus they were given an extremely aggressive specification in terms of performances. I mean, temperature, pressure, specific impulse and thrust for such a small engine, which it was kind of hard to develop initially. But by the moment N1 program was canceled, NK-33s were pretty mature, and that's why they found their use on Antares, and they were flown on Antares prior to the major failure, which resulted in also one of the resupply missions to the ISS. And I don't know, it's kind of difficult to say which was the reason of that failure, because the engines, I mean, the surviving NK-33 engines were physically procured by the US propulsion company, upgraded, outfitted with the modern avionics, so that integration effort may not be an entire success. Did I answer your question?
Pretty much. I had another quick question if that was all right.
Let me answer another one and then I'll come back to you. So Patrick, Patrick Lemon.
Hi, it's Patrick from Bauman University. I think you did not mention it during your presentation, but the N1 rocket had one distinct feature that it used spherical fuel tanks. And I was always wondering, I've never found the technical reason behind it, like why they did not use classical cylindrical scheme.
You see, it, N1 is an extremely fascinating story, because to start the story, it was designed with no purpose in mind, because the scope of tasks was extremely wide, from launching heavy space stations to launching the crew vehicles to Mars and Moon. So but it was a kind of unique project, because some decisions regarding the design philosophy were taken, which were never taken before, and I believe were never taken afterwards, because the lesson was learned. So it had to do with the allocation of the primary launch site in Baikonur, and you should have found a way to take the rocket there somehow, because in case of Cape Canaveral, as you probably know, some kind of the ships and barges were used to transport the ready-made 5 stages to the cosmodrome. Here, the only way was the railroad, and on the railroad you can't transport anything which is wider than 4.2 meters. There is no waterways, the air transportation was not feasible for that purpose, so the decision was made to build the rocket in Baikonur. And the result of for that, the huge assembly facility was based, which essentially was an assembly plant for the rocket. So my understanding of the spherical tanks was that that was the only kind of tank you could assemble in this kind of facility and test there. Because imagine the huge cylindrical tank being welded in the cosmodrome. I think you had to build another production plant for that. So that was one of the reasons, I think. But indeed, the spherical design of the tanks is kind of strange for this kind of rocket.
Right, thank you for your answer.
Mm-hmm. More questions, please? Okay, Curtis, go ahead again.
I was just wondering, do you guys still use kerosene oxygen fuel, or have you upgraded to the hydrogen oxygen?
Well, you see, we are kind of stuck with kerosene and oxygen fuel, because if you take our current launch vehicles, okay. So Soyuz is using kerosene oxygen. Angara is using kerosene oxygen. There is another option we are using on Proton launch vehicle, which is unsymmetric dimethyl hydrazine and nitrogen tetroxide. As for the oxygen hydrogen propulsion, we had some progress in 1970. So if you are familiar with Russian Soviet reusable space system called Energia and Buran, it involved a huge rocket called Energia, which was using hydrogen oxygen propulsion on its second stage. So the technology was developed, but for some reason it's not really used widely. There is a design of the hydrogen oxygen upper stage for Proton launch vehicle, but it was flown by India's space research of organization, but not on the Russian side. So I believe one of the problems is that kerosene and oxygen is a really well-established solution. it's got to do with flying from Baikonur, which has got the facilities optimized for kerosene and oxygen, and the difficulties to deliver and store liquid hydrogen and liquid oxygen at the launch site. But we've got some plans of using hydrogen and oxygen for the heavy version of Angara 5 launch vehicle, which is designed for the new crew vehicle called Ariol, to launch Ariol on the circumlunar or near lunar missions. So the short answer is mostly kerosene and oxygen, and with some prospects of hydrogen and oxygen.
Okay, so it'll be a while before you join us up on the moon, essentially.
Mm-hmm. Okay, more questions, please.
Hello, my name is Baojo. I'm Bauman University student. My question is, can you tell us about why some photos of the lunar surface is brown, but most photos is gray? Thank you.
Well, you see, as a photographer, I can tell you that it might have something to do with the white balance on the imaging payload. Because I can actually, my idea would be is that, well, first, like I think for the white and blue, or I mean white and gray, white, gray, and black, I think it was taken on the traditional film. So if we talk about Apollo imagery, and I think the film was specially balanced for this kind of sunlight. I see where your question is coming from, because if you look at some of the Changi photos, some of them are gray, some of them are kind of brownish. But I think, yeah, I would attribute it to the calibration of the cameras.
Okay.
More questions, please?
Yes, sir.
Yeah, go
I'm
ahead.
Lunar. So the question is how to design a orbit, Earth to Moon orbit. What should we consider?
Could you please repeat the question?
Yes. How to design a Earth to Moon orbit? What should we consider?
So you see, I'm not a trajectory design expert. We've got another purpose, so I would advise to talk to Dmitry Grishko, who is available during this conference again, during the summer school again. But well, from the common sense standpoint, you can actually take various ideas while designing your translunar trajectory. So first, I think you've got to prioritize what you need. If it's critical time-wise, for example, or not, how much of the payload you've got, what are your propulsive capabilities? Because, for example, if you are not time critical and you can use electrical propulsion, which would make the spacecraft way more compact and lighter, but it will take way longer to achieve the moon. If you want to go there fast, I think you can't avoid chemical propulsion these days, and essentially the more powerful engines you've got, the more propellant you spend, the faster you fly.
Thank you.
No problem. Yeah, let me look at the chat, because okay, so never mind. More questions?
Ну что, вопросов больше нет? Спасибо большое, Виктор. Thank you so much, Victor, for a very interesting lecture. Мы будем продолжать с вами работать, и все последующие дни Виктор Валентинович будет работать с нами в других лекциях. Я благодарю от всех участников нашего семинара, нашей школы за то, что Виктор вкладывает так много сил в программу. Большое спасибо. Всем желаю хорошо сегодня отдохнуть. Завтра рабочий день. Мы с вами встречаемся. И, как обычно, встречаемся в онлайн-конференции, но на час раньше, чем сегодня. Завтра в 16 часов по московскому времени мы встречаемся в эфире в культурной программе. Всем спасибо. До свидания.
Thank you very much, Victor. We will keep working, and Victor will be available over the rest of the space school. He will be working with us, the lectures, and I would like to thank Victor once again for putting so much effort into this school and for this presentation. And we will meet tomorrow. We will meet tomorrow at 1 hour earlier than today. So that will be 1600 Moscow time, 4 p.m. Moscow time. See you tomorrow. And it will be a part of the cultural program.
Всем до свидания.
Bye-bye, everyone.
Bye-bye.